Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 7 on decimals, percents, and real numbers. And today we're talking about repeating decimals. So in this section, you'll be able to understand and explain why repeating decimals occur and how to tell if a decimal will repeat, how a fraction can be converted to a repeating decimal, and vice versa, ordering repeating decimals efficiently, and comparing these two numbers, 0.9 repeating and 1. So kind of a surprising fun thing there. So we have examined decimal numbers such as 475 thousandths, which stop and are called terminating decimals. Not all rational numbers can be represented by terminating decimals. So before we continue, I just want to remind you the way to tell whether a decimal will terminate is to look at its fraction form. And once the fraction has been simplified, you look at the prime factorization of the denominator. And if the denominator's only prime factors are 2 and 5, then that decimal will terminate. But if it has any prime factors other than 2 or 5, it will not terminate. For example, converting 2 11ths, obviously 11 is a prime number and it's not 2 or 5, so this will not be a terminating decimal. Converting 2 11ths into a decimal using the long division process indicates that we will actually get 0.1818 repeating, with the digits 1, 8 repeating over and over indefinitely. And you can see where that happens in the long division process. 11 goes into 20 one time. 1 times 11 is 11. 20 minus 11 is 9. Bring down the 0. 11 goes into 90 8 times. 8 times 11 is 88. 90 minus 88 is 2. So we're back to a 2, just like we had here. So when you start to see When you see a number come up in the long division that you've already seen, that means you're looking at a repeating decimal. A decimal of this type is a repeating decimal, and the repeating block of digits is called the repetend. The repeating decimal is written 0.18 with a bar over the 1/8, and that bar indicates that the block of digits underneath is repeated continuously. In this example, you can use a calculator to convert each of the following to decimals. Now, I have to say that a calculator usually works for doing this, but not always. So your calculator display only holds so many digits, usually about 10. So if the repetend is longer than 10 digits, then this method doesn't work. Okay, but in this case, using a calculator, you can find that 1/7 is 0.142857, repeating. That block of 6 digits repeats. And 2/13 also has a repetend that is 6 digits long, 0.153846, repeating. In this example, we'll write 0.5 repeating as a rational number in the form a over b, in other words, as a fraction. So for the first step, we'll call this number x. So x equals 0.5 repeating, so that x is 0.555555, repeating forever. Next, we're going to multiply both sides of that equation by 10. And the reason we're choosing 10 is that there is only one repeating digit. If the repetend was 2 digits, we would multiply by 100. If it was 3 digits, we would multiply by 1,000, and so on. So you multiply both sides of this equation by 10, which gives you 10x equals 5.55555 repeating. Remember, multiplying by 10 just moves the decimal point one place to the right. And now, this is a really clever method for solving this problem. I wish I could say I'd thought of it. Subtract the expression in step 1 from the final expression in step 2. So in other words, we're going to take 10x, which is 5.5555 repeating, and subtract x, which is 0.5555 repeating. 10x minus x is 9x, and 5.5555 repeating minus 0.5555 repeating just gives you 5 because the decimal parts cancel each other out. So 9x is equal to 5, which means x is 5/9. I have to say, I don't really know at what point in school we teach this. I don't remember learning this until I think I was in college. So hopefully that's changed since then, because I think this is a good thing for people to know how to do. All right. Another method, which I don't like as much as the one we just did, it's basically the same thing, but it's using decimals. So instead of multiplying both sides by 10, you can multiply both sides by 0.1, and that will just move the decimal point one place to the left. And it's basically the same idea. All right, s minus 0.1s gives you 0.9s. And when you subtract these two expanded expressions, everything cancels out except for the 0.5, which means s has to be 0.5 divided by 0.9, which is the same thing as 5/9. I like the other way better. In general, if the repetend is immediately to the right of the decimal point, first multiply by 10 to the m, where m is the number of digits in the repetend. So that's what I was saying earlier. If there were 2 digits, you would multiply by 100. If there were 3 digits, you would multiply by 1,000, etc. Now, suppose the repeating block does not occur immediately after the decimal point. A strategy for solving this problem is to change it to a related problem we know how to solve. That is, change it to a problem where the repeating block immediately follows the decimal point. So for example, if we have 2.345 with just the 4/5 repeating, here's what we're going to do. First, we're going to multiply this number by 1,000, which will put the decimal point right after the first 5. So that'll give you 2,345.45 repeating. And then we'll multiply it by 10, and that's to put the decimal point immediately before the repeating part. So you want these two repeating parts to match, because what we're going to do next is subtract these two. 1,000n minus 10n is 990n, and 2,345.45 repeating minus 23.45 repeating gives you 2,322. So when you divide both sides by 990 and then simplify, you get that this fraction is 129 over 55. All right, let's talk about 0.9 repeating. So what I want you to think about is think about 0.9 repeating and think about 1. And how do those two numbers compare? Is 0.9 repeating just a little less than 1? Or is it something else? So I've asked classes this question over the years, and a lot of people are surprised at the answer. So if we use the same method that we were using earlier, since there's only one repeating digit, multiply both sides by 10, or call this thing n, multiply both sides by 10, so that gives you 10n equals 9.9 repeating. Subtract n equals 0.9 repeating, and look, you end up with 9n equals 9, which means that this mystery number n, 0.9 repeating, is actually exactly equal to 1. They are exactly equal. 0.9 repeating is not just a little bit less, it is exactly the same. All right, and that brings us to ordering repeating decimals. Ordering repeating decimals works the same way as terminating decimals. So the only difference is that you might want to write your repeating decimals out, without the bar. usually you don't have to write too much of them. So in this case, we're comparing 1.3478 repeating with 1.34 and then 7821 repeating. Line up the decimals, and then starting at the left, find the first place where the place values are different. So in this case, that is in the hundred thousandths place. The first number has a 3 there. The second number has a 2 there. So that automatically means that the first number is bigger. All right, and then finally, we're going to find a rational number in decimal form between 0.35 repeating and 0.351 repeating. So again, if you write those out without the bar, compare the place values. The first place where they're different is in the thousandths place. All right, and in this case, there is enough room between the 3 and the 1. You could just put a 2 there. So probably the simplest answer is 352 thousandths, but there are an infinite number of other correct answers, like 0.3514 or 0.35 and then 15 repeating, or 0.35136. Okay. So I remember the last time I taught this class face-to-face, I gave the class a little exercise and I challenged them to try to come up with an answer that nobody else was going to think of. And I got some really interesting answers. All right, so that's going to do it for section 7.3, and we'll see you next time.